Hello, and welcome to this lesson on predicting reactivity based on an element's position in the periodic table. In today's lesson, we will firstly explain the relationship between the position of an element in the periodic table and the arrangement of electrons in its atoms. We will then predict possible reactions and probable reactivity of elements based on their positions in the periodic table. First, let's look at atomic number and the position of elements in the periodic table. The periodic table is structured based on the atomic number of elements. The atomic number corresponds to the number of protons in the nucleus of an atom. As you move from left to right across a period, the atomic number increases by 1 for each subsequent element. Now, we'll look at the arrangement of electrons and periods. The electron arrangement of an atom is directly related to its position in the periodic table. Each period, or horizontal row, in the periodic table represents a different energy level, or shell, for an atom's electrons. For instance, in period 2, from lithium to neon, atoms have 2 electron shells. In period 3, from sodium to argon, atoms have 3 electron shells. As you move across a period from left to right, electrons are added to the same shell, gradually filling it up. Now, we'll look at groups and valence electrons. The vertical columns in the periodic table are called groups. Elements in the same group have the same number of electrons in their outermost shell, known as valence electrons. This similarity in valence electrons results in similar chemical properties. For example, Group 1 elements, known as alkaline metals, all have 1 valence electron. Group 7 elements, known as halogens, all have 7 valence electrons. Now we'll move on to our second lesson objective and look at how we can predict reactivity based on an element's position in the periodic table. The reactivity of an element is significantly influenced by the arrangement of its electrons. Specifically, it depends on how easily an atom can gain or lose electrons to achieve a full outer shell, also known as a stable electron configuration. Metals need to lose electrons in order to achieve a full outer shell. Group 1 elements are more reactive than Group 2 because it is easier for them to lose 1 electron than for Group 2 elements to lose 2 electrons. For example, sodium is more reactive than magnesium. Non-metals gain electrons to achieve a full outer shell. Group 7 elements are more reactive than Group 6 elements because it is easier for them to gain 1 electron than for Group 6 elements to gain 2 electrons. For example, chlorine is more reactive than oxygen. Let's now explore the impact of electron shells on reactivity. The number of electron shells also plays a crucial role in determining reactivity. The further the valence electrons are from the nucleus, the easier they are to lose, due to the weaker attraction from the positive charge in the nucleus. This is particularly evident when comparing elements within the same group. In Group 1, sodium is more reactive than lithium. Although both need to lose 1 electron to achieve a full outer shell, sodium has 3 electron shells compared to lithium's 2. The outer electron in sodium is further from the nucleus, making it easier to lose due to the weaker attraction from the positive charge in the nucleus. Similarly, within Group 7, fluorine is more reactive than chlorine. Fluorine's outer electrons are closer to the nucleus than those of chlorine, making it easier for fluorine to attract and gain an electron. By understanding these principles, we can predict how elements will react chemically and the trends in their reactivity based on their positions in the periodic table. This knowledge is fundamental in chemistry, as it helps us understand and predict the behavior of different elements in various chemical reactions. Let's dive into some GCSE level questions to apply our understanding of the relationship between the position of an element in the periodic table, the arrangement of electrons in its atoms, and its atomic number. Question 1. Given the element sodium with an atomic number of 11, Determine its electron configuration and identify its position in the periodic table. Sodium has an atomic number of 11, which means it has 11 protons, and therefore 11 electrons. The electron configuration is 2 electrons in the first shell, 8 electrons in the second shell, and 1 electron in the third shell. So the electron arrangement is 2, 8, 1. Referring to the periodic table diagram, sodium is in group 1, as it has 1 electron in its outer shell, and period 3, as it has 3 electron shells. Let's see this on the periodic table. Question 2. Compare the reactivity of sodium and potassium and explain which one is more reactive. Both sodium and potassium are in group 1, which means they have 1 electron in their outermost shell. Potassium has more electron shells than sodium, so its outer electron is further from the nucleus and more shielded by inner electrons. This makes potassium more reactive than sodium because its outer electron is more easily lost due to the weaker attraction from the positive charge in the nucleus. Question 3. Predict the product when magnesium reacts with oxygen. This question crosses over with some content from our Chemistry Foundations lessons, so check back there if you need some extra clarity. Magnesium is in group 2 with an electron configuration of 2, 8, 2, meaning it has 2 electrons in its outer shell. Oxygen is in group 6 with an electron configuration of 2, 6, needing 2 electrons to complete its outer shell. When magnesium reacts with oxygen, each magnesium atom loses 2 electrons and each oxygen atom gains 2 electrons. The reaction forms magnesium oxide. The balanced chemical equation is 2Mag plus O, 2 equals 2 MeGO. These examples illustrate how to tackle questions involving the periodic table, electron configurations, and predicting reactivity and reactions. Each step involves using the atomic number to determine electron arrangements and then applying that knowledge to understand the element's position and reactivity. Let's recap what we covered in this lesson. We started by looking at electronic structure and the periodic table. The periodic table is structured based on the atomic number of elements, which corresponds to the number of protons in an atom's nucleus. As you move from left to right across a period, the atomic number increases sequentially. Each period represents a different energy level for an atom's electrons, with additional shells being added as you move down the table. For instance, atoms in period 2 have 2 electron shells, while those in period 3 have 3. The vertical columns, or groups, contain elements with the same number of valence electrons, leading to similar chemical properties. For example, group 1 elements, or alkaline metals, all have 1 valence electron, while group 7 elements, or halogens, have 7. Next, we looked at how we can predict reactivity based on an element's position in the periodic table. We discussed how the reactivity of elements can be predicted based on their positions in the periodic table. For instance, reactivity increases as you move down group 1 due to the increase in distance of the outer electron from the positively charged nucleus, which makes it easier to lose. Conversely, in group 7, the halogen's reactivity decreases down the group because the attraction between the nucleus and the outer electrons weakens, making it harder to gain an electron. We will revisit these groups in much more detail later on in this unit. Moreover, by understanding these relationships, we can predict possible reactions and the probable reactivity of elements, which is crucial for studying and understanding chemical behavior.